So, we need to talk about dark matter. Well, my name is Marcio, and I am a PhD student of the Federal University of Rio Grande do Sul in Brazil. My research is to try to understand what dark matter could be. Because I believe instead of list the things that we know, which by the way is just a bunch of few things, it's better to ask the questions about what we don't know what it is. Like, is it a particle? What are its properties? How much mass does it have? And about its angular momentum. Can we talk about some kind of temperature to it? Well, we still don't know. So in this work, we propose to study a dark matter model in which we wonder if some particles that we know really well, like electrons, can interact with the dark matter through some kind of new mediator particle that we're gonna call the Z prime. Here I have to say that there is another Z in their standard model, and that's one of the reasons why we need the prime thing. But we don't know which kind of particle the dark matter is, so we suppose that it can be of three types: an scalar particle, a fermionic particle, or a vector particle, or field if you like it. It all has to do with its angular momentum and other technicalities. Well, it's kind of true that anyone can propose anything for dark matter. Include that it could be, I don't know, big unicorns of the size of the stars orbiting randomly in the galaxy. But it needs to correspond with experiments, so to try to compare our model with the newest experiments, first we need to write down an interaction Lagrangian. And I always have three types of dark matter. We need three of them: a scalar one, a fermionic one, and the most tricky of them all, a complex vector one. For all those three interactions, we can calculate several probabilities for them, using something called the Feynman rules. With that, we now have a very neat set of equations, the so-called total cross-sections, to compare our model with existing results of numerous experiments. But first, we need to translate all those calculations to a computer code. For that, we use the Python language to estimate and analyze the manifold of parameters involved in these calculations, like mass, couplings, energies, and so on. With all that in hand, we finally plot our results. Using some data of great experiments like CMS and ATLAS on CERN and ESA's Planck satellite, we verify, among other things, that in fact we have great chances to produce these particles in the next experiments. For example, for the possible masses of the Z prime boson and the dark matter masses, we still have some huge space of parameters to sweep out. Besides that, there are some good probabilities that we can verify the existence of this kind of processes in the next few years. Experiments like the Compact Linear Collider on CERN and the International Linear Collider on China could verify for the first time the production of dark matter in laboratory. In the meantime, all we have left to do is to keep thinking and wondering, what if? Thank you very much.